Alright, this is Clinton Weir. I'm back to talking about my final project for CSC 535, Deep Learning, um, for University of Illinois at Springfield for spring 2024. So we've last video we talked about model components. These are different kinds of layers that will be used in my convolutional neural network to be used for classifying images. We have 5 different labels, which you can see here: discus, multiple locks, no zip tie, padlock, or zip tied. Also called discus, multiple, unlocked, padlocked, or zip tied. So we talk about convolutional layers, which are, the main component, the main essential component of a convolutional layer. Stacks of convolutional layers. Residual layer, or what I call the residual layer, which is a separable convolutional layer, which is when you use separate for each channel. Residual blocks. The way I wrote this, you're using convolutional, 2 convolutional layers, a max pooling layer, and then you do a residual convolutional layer on the, and then you combine, you add them, and that way, if the signal goes to 0, you can rescue it. Residual blocks, I rewrote the method there, but you have 1 or 2 convolutional layers followed by some residual blocks, and then data augmentation, which has the effect of increasing the size of your, the effective size of your training data. All right, so building basic model. This is the heart and soul. This is what it's all been building up to. We have a number of arguments. First filter count, whatever type of convolutional layers we're going to have in our model. This is the number of filters that will be in the first layer. And as we talked about before, each subsequent layer will have twice as many filters as the one that came before it. So the default is 32, and the number of convolutional layers, convolutional blocks is what I'm calling it here. No, the default is 2. So the first layer would have the 32 filters, and then the second would have 64. And these filters, a filter is, earlier I said a square or a rectangle, but we'll just call it a square for now. It's a square of float values. It's like a square grid of float values. You multiply each value by the value in a pixel, and then you add them together, and that's your signal. And you run that kernel, that grid, across your image, and then across the first row, and the next row, and the next row, and next, and that forms a feature map, and then that goes into the next layer, and so on. And that's how you detect shapes, and that's how you detect larger features, more. And then it goes on down the line. It's how you go from a curved line to to maybe a cat's eye, and then in the then that becomes the cat's face, and then that becomes part of a cat. And so that's how you build up these smaller pieces into larger pieces, and then what you got. So residual layers, this is talking about residual blocks, which is a little different from an ordinary convolutional block, because a residual block has a short circuit around the convolutional layers in the block. If the signal goes to 0 or becomes very small through the convolutional layer, this will bypass it. The input signal will become the output signal, rather than the output. Yeah. Anyway, it short circuits around the block if you use a residual block. Data augmentation we talked about a moment ago, and this is a factor. If the factor is 0, then you're effectively not going to use that. You're just not going to, if you pass a value of 0, then in effect you're not using data augmentation. Okay, so I moved the if I move this piece here to make the model builder code a little bit simpler. Yeah, because I mean, if the factor is 0, you don't even want to put in the layer because it won't do anything. But in that case, let that be decided in the method block rather than in that particular method block for data augmentation, rather than doing it in the model builder to make the model builder a little simpler. Okay, dropout rate. This whole argument could have dropped out because I am not using it, but in theory it would be a dropout is when a signal usually okay so dropout is when you choose to drop out a signal. So like the output of a neuron or the output of a filter might, I think you would call it for filters. I have to check exactly how a dropout works for a convolutional layer, whether it drops out an entire feature map or if it drops out parts of it. I have to look into that. I can't recall. Dense layers, these are the fully connected layers, and they by default we're going to use 1, and this will be between the last convolutional layer, be after that and before the output layer. Of course, every model that we build is going to have one dense layer, at least one, because that the output layer is a fully connected layer. But this argument is about additional layers. Last neuron count 16. So this is kind of the opposite of the convo block count, or the first filter count. The first filter count um, it's the number of filters in your first convolutional layer, and then for subsequent layers, you double it. For neurons, if you assuming you have more than one dense layer, you're going to have some number of neurons in your first layer. You have some number of neurons in your first layer, and then you will divide it by 2 in each subsequent layer. Now, that's fine, but the concern with that is, suppose you divide it by 2 too many times. Divide it, suppose you start with 8, and you divide by 2 once, you get 4, divide by 2 again, you get 2, divide by again, you get 1, and then you divide by 10, well, by 2, again, you got 1/2. And depending on which way you round, I assume you would round up, but depending on which way you round, either you've run out of neurons or you've got 1. If you got 1 neuron, I don't think a single neuron is going to be very useful. Just leave it at that. So that's the issue. The way I'm tuning, I don't want to worry about that. So, if you look at it in, you can just look at it in reverse. What is the last? What's going to be the number of neurons in the last layer? And then you double it for each previous layer, and then you don't have to worry about the number of layers becoming ridiculously small. They're not going to become smaller. They're going to become bigger from the number that you choose to pass in this argument. So, suppose you have 5. You have the number 5. Instead of dividing, of course, from 16, you divide 5 times, and you've got, what, 1/2, I think. So instead, you multiply it by 2 5 times, and gosh, maybe I think that might be 512. 16 times 2 to the 5th, 512. And that's a lot. That's quite a few neurons for a layer, depending on what you're doing, of course. But that's better than getting like 1/2. So it's a little safer, is my point. Also, if you've got 5 layers in the output layer, if you got 5 neurons in the output layer, I don't think you want to have fewer than 5 neurons in the preceding layer. I'm not sure. I don't think that's a good idea. In any case, and then I have an argument for the dropout rate in the dense layers. Default is 0. And that means, suppose you have a dropout rate of 0.5. Then in each of your dense layers, your fully connected layers, during training, there's a 50% chance that any particular neuron will output 0, even if, regardless of what its calculated signal thing is, it'll just drop out. It'll output 0. And that is a regularization technique. It reduces overfitting, which is to say it reduces the gap between the training loss and the validation loss. All right, moving on. Input shape. We talked about the image size, and this is not the raw image size. I think I said that. This is, the images are going to be resized, and I'm not sure whether that's done. I assume it's done during this process here, where it's establishing the data set rather than here, but I'm not certain. And then the input shape, and then so the first two values are the dimensions, and the last is 3 because there are 3 channels, which is to say there are 3 components of the color, which might be red, green, and blue. Not sure. I'm not entirely sure. So through this function definition, the signal is going to be called x. X is going to be the signal. And you've seen that already during the component definitions, the layer definitions. So we got the signal will go through a data augmentation layer. If data augmentation has been activated or enabled, or whatever you want to call it, if the factor passed, if there is a factor passed that is not 0 or greater than, rather if it's not less than 0, or let me say that again. If data augmentation factor greater than 0 is passed, then you will get this, I guess, is it 3 layers? I suppose it's 3 layers, huh? But it'll pass through these layers to transform the image in one or more of various ways. Next is a rescaling layer. The values of the pixel, the values in the 3 channels will be numbers between 0 and 255, and this will scale those numbers down to be float. I mean, it says it right on the screen, but it will rescale the numbers, the color component numbers. It'll scale those down to the range of 0 to 1. That is useful. That is, I think it's pretty useful. I think it's pretty useful to control the scale of other numbers. The control. All we're doing is toying with numbers. We are multiplying. We're just multiplying numbers, adding numbers. And I mean, it's numbers all the way down. It's kind of crazy if you think about it, because this, we got this picture, and it's these latches or whatever. It could be a picture of anything. And to the human brain, that's a padlock, that's a this, that's a that. But to a computer, it's just a series of numbers, just like anything that a computer deals with, just numbers all the way down. And that's what we're working with here. We're multiplying and adding numbers, and it's mysterious. Like, why, when you multiply this number by that number and you add it and and you have millions of numbers that you're just chugging through, and somehow you end up with, hey, that's a padlock, or it's mysterious. It is, that this bunch of numbers multiplied by that bunch of numbers, somehow the computer knows, hey, that's a padlock, that's a discus lock. It's mysterious, but constraining numbers, constraining the values. I don't. I'm not certain. I'm not certain that it makes that much of a difference whether we represent these floats as being between 0 and 255, or 0 and 1. As long as we're dividing them all by the same number, so they're going to be relative to one another, whether they're identical. You could represent the numbers from 0 to 255. You could represent those numbers in the in computer science. You could have over here well, maybe not. Maybe I'm talking out my butt, but you could represent the float, 255 floats, 256 different float values over here, and 256 float values over there, and they could be the same bit representations, and one of them could be the numbers from 0 to 1 in steps of 1 over 255, and the other could be float numbers in the range of 0 to 1 in the steps of 1 over. I think I messed that up. So you have the same bit representations. Over here, it's 1 to 250. It's 0 to 255 in steps of 1, and over there is 0 to 1 in steps of 1 over 255. They could be the same bit representations, and it's just the same bits, same sequence of bits on both sides, and we are perfectly capable of recognizing this. The two, one of the lists is an integer from 0 to 1 to 255, 0 to 255, and over there, we can recognize them. We can recognize a bit sequence. We can define a bit sequence to mean whatever we want. And we can define a system. We can define many systems of to represent many different things with the same bit sequence. It's almost entirely in how we decide to interpret the bits. It's almost entirely dependent. What bits mean. It's almost entirely what we decide they mean. So, in this case, we've decided we want these numbers, these integers from 0 to 255. We've decided we want colors to be represented by by 3 numbers between 0 and 255. And that's great. We can all work with that. And when we're building images, it's fine. It works great. In this particular case, we've decided we want to work with floats rather than integers, and we've decided we want to work with floats between the numbers 0 and 1. So we have one context where the colors are represented by integers from 0 to 255, and now we're converting that convention into this other convention where the colors will be represented by floats from 0 to 1. And in a sense, the representation of colors using the float values from 0 to 1 makes a lot more sense, because how much green is in this pixel, for example? Is it the minimum amount, which is 0, like you don't see green at all? So you're gosh, I don't know if I think it's cones. If the cones in your eye are not going to see, the ones that detect green, they're going to see no green. They're not going to be activated. The cones in your eye might be rods, I don't know, but that would be 0. Now, suppose there's a whole lot of green. The maximum amount of green that the computer pixel can output, the maximum amount, that would be 1. That would be 0 to 1 is the percentage of the maximum amount of green light that the display can output at that position in that image. So 0 to 1 makes a lot of sense, but the reason, obviously, that we're converting from these integer representations to this float representation, it lends itself to neural network, to training a neural network. Why that is honestly, it's beyond me. But it is my impression that we generally want to work with floats in the area 0 to 1. So I need to study that a little bit more, perhaps. But 0 to 255, 0 to 1, it's all the same. It's just different ways of saying the same thing. Let's move on. Stacks of convolutional layers, convolutional blocks. By default, we are going to make convolutional blocks. That's standard blocks, not these separable blocks that I don't think we even use. I don't think I correctly implemented. I don't think I actually have anywhere that uses the residual layers, the quote-unquote residual layers, the separable convolutional layers. I've defined them, but I think I left them out of, they're not ever used in my neural networks. But these residual blocks, though, they are I think I'm getting a little bit off, but okay. So by default, we're going to use convolutional blocks. That's as opposed to residual blocks. And so that's the default. If you don't indicate a number of convolutional blocks, and you don't indicate a number of residual layers, you're going to get convolutional blocks. If you pass a number for residual layer count, then you're going to get residual blocks. It's going to ignore your convolutional block count if you pass them both. So that's what's going on here. We've already looked at the residual blocks and count in the convo blocks. We've already looked at both of the definitions for those functions. Global average pooling, that is going to flatten the output of the filters it's going to flatten the outputs, and then with that flattened, with this data flattened, you can then pass the data to a dense layer or a fully connected layer. And by default, we will use one dense layer with 16 neurons, but dense layers, you can select how many you want. So the range looks a little funky. The range function call, what this means is that the reason why you're counting backwards is right here, is this 2 to the power of dense layer. This is because the correct number of neurons in the first layer is the number of neurons in the last layer times 2 to the power of the number of total layers. So if you have one layer, then it's 2 to the power, I might have said that wrong. So it's the number of layers in the last layer, last neuron count is 16. So if you only have one layer, then you want to multiply by 2 to the power of 0. So dense layers would be 1. 1 minus 1 is 0. We're talking about if you have one layer. So dense layers minus 1 is 0. So you want to so last neuron count 16 times 2 to 0 is 16. 2 to the 0 is 1. So 1 times 16 is 16. So dense layers minus 1 is 0. And the reason, there's a reason why this second argument is -1. If it were 0, if you're, so you have a range of 0 to 0, then that loop would completely be skipped. It needs to be 1 beyond. This number needs to be 1 beyond the minimum the extrema, and we're counting it backwards. So this looks bizarre, perhaps. This looks kind of crazy, but it does work. I probably should have expressed this differently, but the point of this is to get to the last layer and have it have a number of neurons that is equal to the argument passed, the number passed for the argument last neuron count. That's the ultimate goal, to have the right number of neurons in the last layer, and then have double that in the previous, and double that in the previous, and double that, and so on. Now, ironically, when I tune, I'm getting ahead of myself again, but ironically, when I tune the number of dense layers, I got 1. So this whole thing could have been avoided. Of course, then, I wouldn't have tuned the number, and so I wouldn't know it was 1. But I could replace this and just say x equals layers. I could and then have this dropout layer, and that would have the same effect. That would have the same basic effect, because when I tuned the neuron count, I get 1. I get 1 is apparently the right number of neurons. Now, but I'm still going to leave it. All right. So the last layer in the model building function, the last layer in every model is going to be the output layer, of course. The number of neurons is 5 because we have 5 categories, 5 classes, and so this is going to be 5 probabilities, each one corresponding to that class. And the probability that is the largest will be the class that is predicted. And but for now, what we're doing, we're outputting 5 probabilities, 1 for each class. We're going to compile. So the model is this is maybe that's why this says it's never used, because here I'm saying model, I'm defining Karastop models. Anyway, let's get back to what I was doing. Where was I? Okay. Who knew I could get that lost? Okay, so this says Keras. No, this is not what I was looking at a moment. This is not the thing from the imports or whatever. So this will define a model with the input that I specified, with shape, with this shape here, and the output. So after we passed the signal through this layer and that layer and so on, the output is the dense layer with 5 probability values. So that's how the model is defined, with the input value and the output value. Then you compile it. We're not one-hot encoding the labels. Where each label is a integer from 0 to 4, representing the 5 different the 5 different classes. So that's why we're using a sparse categorical cross entropy. The label is categorical and is considered sparse, like I just said, because it's like an index. The labels are indexes, not one-hot encoded values. So potentially, suppose that we started with probabilities. Suppose that for each image, we were unsure as humans what the image was, what label. Then we might use one-hot encoding. Is that right? In any case, that's another option. To use one-hot encoded, and then that's a different law. Then use a different loss thing. Metrics is accuracy. I don't really use that. I do keep track of the loss. I'll have to look into why. I'll have to look into that. That's interesting. I mean, I do track the accuracy. I do. I think I use accuracy. I have to figure out why it is able to keep track of loss, even though I don't have loss listed here. That I'm not sure about. Then the optimizer is Atom. This is just basic optimizer. It rather than customizing it, I just left it alone. Then you return the model, and then this object that you get back, you can start training with. And that's what we'll do next.